Okay, so in 1.1 we defined what a limit is. We talked about how to find it from a graph. We defined continuity by using limits, talked about discontinuity, and then we talked about how we could use direct substitution to find a limit if the function was continuous over the value we were trying to find the limit of. So this section is going to lead us to what happens if we're trying to find the limit at a value where it's not continuous. How can we do that? So 1.2 is going to be on methods for computing limits and determining continuity. So if you look at problem 1 down here and you try to evaluate this limit as x approaches 0 of x over x squared plus x. If you tried to evaluate that using direct substitution, we would end up with what we call indeterminate form. So indeterminate form is basically 0 over 0, and I'm putting that in quotations because you really should never write that. It's terrible notation, but that's what you're seeing mentally when you're trying to use direct substitution. So frequently when we're trying to use the direct substitution method, we'll come across something called indeterminate form. There are other forms besides just 0 over 0. We'll talk about infinity over infinity or other cases later, but today we're just going to be talking about the indeterminate form of 0 over 0. So when we get something like this, our gut instinct should be, is there a way that we can simplify the expression or the part of the function that we have so that when we simplify it, we no longer have 0 over 0, and then we would be able to use indeterminate form. So that is the goal. There's 3 pretty basic strategies to kind of look for when you're first starting these. The first one is factoring. Can we factor the numerator and the denominator? And by doing that, do we then simplify to something that we can use direct substitution on? So that's sort of the first strategy. Another algebra tool that we can use is using the conjugate. If we have some sort of radical in the bottom that's creating 0 in the denominator, if we're using direct substitution, then it is possible that we just need to multiply both the numerator and the denominator by the conjugate, and that could solve our issue of getting indeterminate form when we're using direct substitution. One of the other commonly used techniques that we can try out to help us when simplifying to eliminate an indeterminate form issue is using special trig limits. There are lots of things that you could think of there. You could think of using sine squared plus cosine squared equals 1, any of your base trig functions and trig identities that you learned in previous classes. Also, 2 that you're allowed to use without having to show any work for are these 2 in red. One of these we talked about yesterday. The limit as x approaches 0 of sine of x over x is 1. The new one today that we're adding in there is the limit as x approaches 0 of 1 minus cosine of x over x is 0. Sorry, that's a kind of an ugly 0. There we go. So these over here are things that you should memorize so that you can use them without having to think too hard about them. Okay, so we're going to go ahead and look through some examples where we may need to implement one of these strategies. So if you look back to number 1, the first thing that I notice is that this is in fact going to factor. Every time you simplify a limit before you use the direct substitution step, you need to make sure you're using this notation where you still have the limit. At no point in time before the direct substitution step are you allowed to stop writing the limit as x approaches whatever value. So here I can factor an x out of the denominator. I can simplify that. That's going to give me the limit as x approaches 0 of 1 over x plus 1. Now I'm going to use direct substitution. So I no longer need to write the limit as x approaches 0 because I'm actually directly substituting in. And when I do that direct substitution, I'm going to get 1 over 0 plus 1, which is just going to be 1. Now, at this level, this step right here that I'm going to underline in red, you really don't need to show that middle step where you're actually factoring out. It's totally fine for you to go from the original problem to the part where you already simplified out the factor that divides out and then directly to the answer. You're at a high enough level of math where you really don't need to show every single step of factoring along the way. So why don't you go ahead and pause this video and try and work through number 2 using similar logic. So looking at number 2, the first thing we would try is direct substitution. If I use direct substitution, I'm going to get indeterminate form. I'm going to get 0 over 0. So I want to try and manipulate x minus 9 over x squared minus 81 so that it simplifies to something where I am then actually allowed to use direct substitution. So I know that that denominator is going to factor to be x plus 9, x minus 9, which means the x minus 9s are going to divide out. And I'm going to be left with the limit as x approaches 9 of 1 over x plus 9. Then I can use direct substitution, and that's going to give me 1 over 18. Number 3, again, is going to result in indeterminate form if I use direct substitution now. Sine of 0 is 0. 2 times 0 is 0. Since I see that there is a sign there, I know I'm going to try and use some sort of trig function or trig property to help me out here, and that trig property is going to be this one. So I know that the limit as x approaches 0, which is what I'm approaching on number 3, of sine of x over x is 1. My problem is that I have a 7 and a 2, and if they were both 7s, then this property would still hold. The limit as x approaches 0 of sine of 7x over 7x would still be 1, holding to those same algebraic properties. So what I want to do is get 7x in the denominator. So what I'm going to do is I'm going to multiply this limit by 7 over 7. I'm multiplying by 1, so that's not changing the value of the limit. And the way I'm going to write this so that I can use that property is the 7 I'm multiplying in the numerator, I'm going to write in front. I'm going to leave my sine of 7x where it was. I'm going to rewrite my 2 in the front. And I'm going to combine the 7 that I multiplied the denominator by down here. The reason I want to do that is because now I can say that sine of 7x over 7x, the limit as x approaches 0 of that, is going to be 1. So that's just going to simplify to be 1. Then I'm looking at the limit as x approaches 0 of 7 over 2, which x is not changing anything there. I just have a constant. That limit is just going to be equal to 7 over 2. Continuing on to number 4, even though I don't have a radical in the denominator, I still have a radical somewhere. Therefore, multiplying by the conjugate could help me potentially eliminate indeterminate form. Because right now, if I substitute 1 in, I am going to get indeterminate form of 0 over 0. So let's just see what happens if I multiply both the numerator and the denominator by the conjugate. I can now take this one step further. I can divide this term to be 1. So this leaves me with the limit. Again, you have to write the limit. You can't just jump to say that this is 1 over the square root of x plus 1. You have to write the limit. The limit as x approaches 1 of 1 over the square root of x plus 1. Now I can use direct substitution. That's simply going to give me 1/2. Number 5 is interesting because it's asking us about a one-sided limit. So in this case, we're not going to factor anything. There's no conjugate. There's no special trig limit that's going to help us here. We just need to analytically think about what is happening. So if you think about what's happening in the numerator, as x is approaching 2 from the left, I'm at 1.99999. It's getting closer and closer and closer to 2. And if I'm plugging in 2 or just right before 2 into the denominator, I'm going to have negative 0.00001. I'm getting closer and closer and closer to 0, but from the negative side. So if you think about what's happening with this fraction, the top is getting bigger, the bottom is getting smaller. If you think about the growth at which the rate at which they're changing, which means that this limit is really not going to exist. We're going to talk about later how this could also be thought of as the limit being negative infinity, but since we haven't gotten there yet, we're just going to think about this as the limit does not exist. Go ahead and try using the conjugate on number 6 and see if you can figure out some trig identities to use to help you out on 7, and then unpause the video. So looking at 6, we're going to multiply by the conjugate. The limit as x approaches 23 of x minus 23 quantity times the square root of x plus 2 plus 5. And if you look at the denominator, that's going to end up difference of squares becoming x plus 2 minus 25. This is x minus 23. So those factors are going to divide out, which means I no longer have a denominator, which means I no longer have to worry about indeterminate form. Since I no longer have to worry about indeterminate form, I can just use direct substitution. That's going to give me the square root of 25 plus 5, which is going to be 10. Hopefully, when you look at number 7, one of the first things you think when you see tangent is that tangent could be rewritten as sine over cosine. Once you have that rewritten, you can see the limit as x approaches 0. In part of this function, we have sine of x over x, which we know that that portion is just going to become 1, which means we're going to have the limit as x approaches 0 of 1 over cosine x, which we can use direct substitution for because cosine of 0 is just 1, so this limit is just equal to 1. So if you're watching this video and we're not in class together, you have a number 8 on your paper. If we were in class together, that was going to be our warm-up problem because this actually uses a lot of stuff from last class. So pause the video, see if you can work through number 8, remembering that what matters is what's happening at this value of 2. So remember, in order for f to be continuous, we need the limit from the left to be equal to the limit from the right to be equal to the value of the function at 2. So the first thing we're going to look at is what is actually happening at 2. At 2, f of 2, we're plugging into this bottom piece of the function, and that's going to give us negative 1. That is also going to be the limit from the left of the function. So limit as x approaches 2 from the left of f of x is also negative 1. So what I need is, I need the other piece of the function to be negative 1. That's what would make this continuous, because this part is the limit as x approaches 2 from the right of f of x. We want these, all three of these pieces to be the same. So now we're just going to do some basic algebra to solve for a, remembering that we can actually substitute in here. We're not having x just be x, we're having x be 2. So if I substitute 2 in, I'm going to get 2 squared is 4, 4 times 3 is 12, 12 plus a is negative 1, so a is going to be negative 13. So the value of a that makes this function continuous is negative 13. So now we're going to move on to probably one of the most important theorems, one of the most foundational theorems in calculus. I think it's pretty intuitive when you explain it, but if you're watching this video, there's a great visual. You actually have to go into my slideshow to find the link to that video, or to that Desmos portion, but it helps you sort of manipulate and drag and see the visual of what we're about to talk about. But hopefully I can explain it well enough that you don't need a second visual. I know most of you could Google or look on YouTube and find a video that shows it a little bit better as well, but I don't think you're going to need that big of a visual. Okay, here we go. So if we have a continuous function, or on some interval, some closed interval, meaning we know what happens at the endpoints. We know what's happening at the beginning and at the end of that part of the function. The intermediate value theorem says that every value in between what's happening when the function is evaluated at those endpoints is included. So, okay, we are now going to talk about the intermediate value theorem, commonly abbreviated as IVT. I'm going to read it to you. I'm going to help kind of explain what it means visually. I think it's pretty intuitive, but if you're looking at this through the slideshow, you'll see it says, here is a visual. That's a great place to go on and click, and it takes you to a Desmos area where you can actually kind of manipulate and play with the function. If you're seeing this class live, then you already have seen that. So here's what the intermediate value theorem says. If I have a continuous function f, and it's continuous on the closed interval from a to b, so that is wildly important, continuous, and there is some k value that's within the y values from a to b, then there must be at least one x value, we're going to call that c, between a and b such that f of c equals k. Okay, that's a whole lot of math notation. What that's basically saying is, if I know that this interval, and let's just put some numbers here. Let's say that f of a is 2 and f of b is 9. K being some number between 2 and 9, like let's say 6. What that's saying is every number between 2 and 9 has to be covered because we are saying that this function is continuous. If it's continuous and it's going from 2 all the way up to 9, at some point in time it has to cross the number 6. You'll notice it says at least once because it's possible that maybe we have a function that's doing some sort of odd things and maybe it crosses more than once. But this question or this theorem is telling us if we have a continuous function on a closed interval, every value between those two y values will be covered at some point. So when you are using IVT, you need to make sure that you are always verifying that condition, that it's continuous on the closed interval, and you need to make sure that you state IVT by name. So I'm going to show you exactly what that looks like on these examples here. So first of all, f of x is a polynomial. So I'm going to start by just saying f of x is continuous. You don't have to say why it's continuous. You don't have to prove that it's continuous. When you're doing this, you're really speaking to math people. Math people understand that x squared minus x is continuous. So now I need to know what is happening at the ends of this interval. So what I'm going to do is I'm going to figure out what's happening at the beginning and what's happening at the end. So f of 0, if I substitute 0 in, I get 0. F of 5, if I substitute 5 in, I get 20. So what this means is, since f is continuous, between 0 and 5, I am hitting all of the numbers between 0 and 20. So between my x values of 0 and 5, I'm hitting all of the y values from 0 to 20. This particular question is asking us, is there some value of x between 0 and 5 that gives us the value of 12? Well, there has to be. If I'm going from 0 up to 20, at some point, since this is continuous, I have to pass through 12. So the answer is yes by IVT. And it says, if so, find the c value. So that really just means I need to set 12 here and solve that quadratic, which I know you know how to do this one nicely, factors. I'm going to just tell you, when you solve this, you actually get that x is equal to 4 and negative 3. Negative 3 is irrelevant because it's not on the interval. So the c value, I should say, that gives you 12 is 4. So similarly on number 10, the first thing we need to do is we need to verify the conditions in order to use IVT. So we need to state that it is continuous. We need to make sure it actually is. So this function is not continuous everywhere. Depending on the interval, it could be continuous and we could use IVT. So let's look at what we're looking at. We're looking at the interval from 0 to 3. Well, this is not continuous at x equals 2. So this is not continuous on the interval from 0 to 3, so IVT does not apply. We're not saying that there isn't a value that gives us the output of 4. We're saying that the intermediate value theorem does not guarantee that there is a value. We can't use it to justify that in this case. So these last 4 problems I'm not going to walk you through. Those are extra practice for you to try out on your own. I will show the work in just a minute up here so that you can see it. And I hope that you really understand how to simplify using algebra, conjugates, factoring, or trig limits to help you evaluate limits you couldn't evaluate because of indeterminate form. And I hope that you have an understanding of how you can use the intermediate value theorem and when it applies. So here are those worked out problems. You probably want to pause the screen so you can look over the solutions and let me know if you have any questions. Thanks.